So now we're going to begin to apply equilibrium in some very specific situations. The first situation that we're going to look at is the common ion effect, which involves, just like it says, it involves a common ion in the solution. When the salt with the anion of a weak acid is added to that acid that's already in equilibrium, it reverses the dissociation of the acid. So in other words, if you had acetic acid in equilibrium with the acetate ion, and then you put in sodium acetate into that system, the acetate is actually, according to Le Chatelier's principle, going to cause that reaction to shift to the left, and that's going to reverse the dissociation. You'll have less dissociation of the acid. The same can happen then with the salt with the cation of a weak base, same situation. And what you would do for both of these is you would simply use an ice table, but in the ice table you wouldn't necessarily have in the case of a weak acid, you would have the concentration of the acid, but you would also have the concentration of the anion initially. So you would have the concentration, let's say, of acetic acid, and you would also have a concentration of acetate ion to start, rather than just having the acid concentration to start. And then you would use an ice table, like you normally would with an equilibrium system, to calculate the concentration then of all the species once equilibrium is actually reached. Now, a real common ion effect situation is a buffered solution. A buffered solution is a solution that resists a change in pH. It has a weak acid and its salt, so there's your common ion effect, or it has a weak base and its salt. We can make a buffer of any pH by simply varying the concentration of the two solutions, the weak acid and the salt, or the weak base and the salt. Again, calculations with a buffer are done using an ice table, because this is an equilibrium system and this is a common ion effect. So here's an example of a buffer. Calculate the pH of a solution that is 0.5 molar acetic acid and 0.25 molar sodium acetate. So you have your weak acid and then you have the salt of the weak acid. Now sodium is a spectator ion, and so that species just drops out of our reaction. So what we're worried about here is the weak acid equilibrium. Notice initially I have the acetic acid 0.5. I have no H plus solution, no H plus in the solution, and then I have a 0.25 m molar concentration of acetate. So we would then do our change in X like we normally would. So the change in X there is going to be minus X for the acetic acid, and then the H plus and the acetate are both going to go up by X. So we end up with 3 equilibrium concentrations, and we would put these then into the Ka expression like you normally would. So we want to do the math using the Ka. The Ka for acetic acid is 1.8 times 10 to the negative 5th. So we're going to set up our H plus concentration and acetate ion concentration over our acetic acid concentration. And then we can assume X is tiny because of the Ka, as we have done in previous ice tables. So you can leave out both changes in X, the plus X on the top and the minus X on the bottom, and then simply do some easy algebra and solve for your X. Now again, if you don't want to do that and you want to graph it, or if you want to use your solver, or if you want to use the quadratic, feel free. So our X is 3.6 times 10 to the negative 5th. Because we estimated this, we would go back and make sure that it's less than 5% of the two values that it was subtracted from or added to. And it is. So our assumption is valid. So we would take then, because this X represents our H plus from our ice table, we would take the negative log, and the pH would be 4.44. That would be the pH of our buffer. So again, we did the ice table. We just had an initial acetic acid concentration, and we also had an initial acetate ion concentration. Now, what happens when you add a strong acid or base to a buffer? You do the stoichiometry first. So you figure out that strong acid how much of the base is it going to consume, or with a strong base, how much of the acid is going to be consumed. A strong base will grab H pluses from the weak acid, which reduces the amount of weak acid in the equilibrium. So you have a Le Chatelier's situation there, and the strong base is your stress. If you add a strong acid, it will add protons to the anion of the salt, and that reduces the A- concentration. Again, this is Le Chatelier's principle. So the strong acid and the strong base are shifting the acid base equilibrium. And then you simply do an equilibrium problem once you've done the stoichiometry with the strong acid and the strong base. So we could take a look at one of these situations. What is the pH of a 1 liter solution of the previous solution when 0.010 moles of solid sodium hydroxide is added? So how will this influence then our buffer? So what that NaOH will do is it will consume some of the hydrogen from the acetic acid, and in the initial mixture we added 0.010 moles of sodium hydroxide, so it's going to reduce the acetic acid by 0.01 moles, and it's going to increase the acetate ion by 0.01 moles. So the 0.49 m would represent our new acetic acid concentration, and the 0.26 m would represent our new acetate ion concentration. And then this was in 1 liter, so we could simply divide both of the moles by liters and get our molarity. Now, then we would of course set this up in an equilibrium system and do an ice table. So we start out with 0.49 acetic acid, 0.26 m acetate. Again, this is going to shift to the right because we have no H plus there initially. So we get a change in X. We would then do the math in this equilibrium system using the Ka. Once again, if you want to estimate here with the plus X and the minus X, you can do that. That simplifies the math. Our X ends up being 3.4 times 10 to the negative fifth. Our assumption is valid, assuming the X is tiny, and we end up with a pH of 4.47. Now, notice, if we had added 0.010 moles of sodium hydroxide, the pH would have been 0.010 m OH minus, POH would have been 2, so the pH would have been 12. But with a mixture of the acid and its conjugate base, the pH does not change very much at all. That mixture then is called a buffer. Now recall, the buffer that we calculated the pH of was 4.44, and then after adding the base it had only gone up to 4.47, so very little change there. We do have a general equation that we can use whenever we're working with pH, and especially pH with buffers. And this is called the Henderson-Hasselbalch equation. Now the Henderson-Hasselbalch equation is a derived equation, and this is kind of showing you the derivation of that equation. So it starts with a Ka, rearrange the Ka, put the log in there so that you have the pH, and at the very bottom of this screen you're going to see the derived Henderson-Hasselbalch equation. pH equals pKa plus the log of A minus over HA. So anytime you have a buffer and you know the concentration of the acid and you know the concentration of the salt, you can simply plug it into this equation and you can generate the pH very, very easily. This is our Henderson-Hasselbalch equation. Works for an acid and its salt, and that would be something like HNO2 and NaNO2, or it can also work, of course, for a base and its salt. Just make sure in that ratio there, A minus over HA. So you want the base on top, you want the acid on the bottom. So we could use it for something like NH3 and NH4Cl. Now, a buffer has a certain capacity, And you have to be careful with buffers. You can't add too much acid or too much base because you'll go past the capacity. As long as the ratio A minus to HA in the buffer doesn't change a whole lot, the pH won't change. The more concentrated these two are, the more H plus and OH the solution will be able to absorb. So in other words, if you had a buffer where the A minus and the HA were both 1 molar, that solution would be able to absorb a lot more acid and base than if you had a buffering solution where each one of those, the A minus and the HA, were 0.1 molar. So the more concentrated those two parts of the buffer are, the better buffer you have. So larger concentrations, bigger buffering capacity. So let's take a look at a situation like this. So we could calculate the change in pH when we add HCl to these two buffered solutions. First we're going to add it to the 5 molar solution of HAC and NaC. As we go through all the math here and calculate the pH, we get a pH of 4.74. So we've taken a buffer and we've added HCl to it, and we have a pH of 4.74, which is pretty close to the pH of the buffer beforehand. Now, if we take a less concentrated buffer, so now it's the same buffer, it's acetic acid and sodium acetate, but it's 0.05 m, and we add our acid to this solution, we get a pH of 3.79. Now again, this is compared to the 4.74. So the 5 molar buffer, much more able to absorb the acid than the 0.05 m buffer. So again, the more concentrated the buffer is, the better it's able to absorb acids and bases. The best buffers have a ratio of A minus to HA equals 1, so they have the same amount of A minus as they do HA. And this happens to be the situation where the buffer is most resistant to change. And this is true, of course, when the A minus is equal to the HA. And in that Henderson-Hasselbalch equation, that would be when the pH equals the pKa, since that ratio A minus over HA equals 1, and in the Henderson-Hasselbalch equation you are logging that goes to 0. So when the pH equals the pKa, this is the best possible buffer.